Okay, so we're going to be covering just chemistry in general. We're going to talk about phases and matter. We're going to talk about the physical properties and the chemical properties. We're talking about measurements, uncertainty, accuracy, precision, all those things. So, what was I going to say? Let's get started. Okay, so the definition of chemistry is basically real simple, right? It's the study of composition, properties, and interaction of matter. That's initially how everything started. We all talk about matter. Matter is what matters, right? Okay? Now we've been doing chemistry and we've been looking at matter for thousands of years, and here it says, 2,500 years. I'm going to say probably even longer. In the early days, Greeks defined matter basically based upon the four elements. They thought everything was made of either the earth, the air, fire, or water. They didn't quite understand that, there were particular elements, right? So those were the four basic elements initially. But then alchemists, who always wanted to change things from some stone to gold, right? They start realizing that there are metals, and that there are some metals that are really valued, and there are other metals that are really volatile. And we're going to be talking about that. And so we kind of come a long way in terms of understanding aspects of the elements. Now, chemistry is the center of the world. Whether you like it or not, you can't get away from chemistry. You drive down the road, you're dealing with chemistry. You go shopping, you're dealing with chemistry. You eat, you're dealing with chemistry. So we touch every aspect of your life, whether you like it or not. So it's probably a good idea to understand chemistry, since we're going to be using it for everything. You guys can see my screen. I'm not just talking to, right?
Yeah, we can see your screen.
Okay. Yeah.
What was I gonna say? So, I have a friend and we argue a lot. He's a physicist. I'm a chemist, right? Or say I have a degree in chemical engineering. I also have a degree in biology, right? I know that chemistry touches every aspect, right? One of the reasons why I love chemistry. I know a lot of biologists who avoid chemistry, but did you say you? Well, you can't avoid it. It's part of you. You can't avoid it. Embrace it. And the key is right now, if you embrace it right now, and I know it may seem hard and difficult and all those things, but if you embrace it right now, learn to love it, it's kind of like an arranged marriage for everyone. Whether you like it or not, it's an arranged marriage. You got to learn to love it, okay? And so if you do that now, it's going to make your life so much easier, I promise.
No divorce.
No divorce. Yeah, you can't divorce chemistry, okay? So, as I told you, chemistry is seen in every aspect of your life, from food digestion to synthesis of polymers. So you guys wear synthetic clothing, right?
Mm-hmm.
The pots and pans that we use, our credit cards, our money in a lot of ways, right? So whether we like it or not, again, we are dealing with chemistry. We can't avoid it. And that's the whole thing. Now, if you guys take a moment, I want you to take one moment and think about some aspect of chemistry that you've just experienced within the last day or so, or even this morning when you got up, maybe. Okay, so Maddie, tell me one aspect of chemistry that affects your life.
Well, I brush my teeth.
You brush your teeth, okay? So tell me how, in what ways?
Well, I'm assuming a chemist came up with my toothpaste, and it has whitening powers, so that's extra.
Oh, excellent.
And it blends with water to clean my teeth.
Okay, perfect. Preston.
Yes, sir.
Tell me, how has chemistry affected your life?
Just through one of the basics that comes to mind, like just waking up. electrical impulses sent from the CNS to the PNS, just stuff like that.
I think that's great. That is great. Eddie,
Yes.
how does it affect your life?
Yeah, I was thinking the same thing, but like in a different way, as the same person said it. Instead of brushing teeth, like with washing clothes,
Oh,
like
cool.
the chemicals, they get rid of the stains and everything.
Yeah. Okay. So whether we like it or not, chemistry is going to affect your life. Okay.
Mm.
So in this course, you're going to kind of learn how that happens. And I want you to think about that. That's part of your project. You guys know that you guys have this Uber project that's going on. I'll give you more details about it a little bit later. But I want you to sit there and think how chemistry is happening at each of the stages, And when you start thinking about that, you're starting to figure out like, oh, how's that working? How does that work? How do we provide nutrients to plants? How do we synthesize the fibers on our toothbrush? Right? When you start thinking about that, you'll sit there and you'll find chemistry to be more interesting than it's ever been before. Rather than a barrier, it is going to be your ally. Okay? Okay, so we are in science. And the best thing about science is a lot of things that we figured out weren't figured out before, and a lot of things that we will figure out aren't figured out now. Like, for instance, there's this really crazy disease going on right now, right? Caused by this virus that we call COVID-19. Every week, if you're reading the scientific publications, you find out a little piece of information. Every week, we found out that something that we believed a week ago was BS, right? And this here is what science is about, right? It's figuring out that a lot of the times that what we believe, it's BS. But we need ways of figuring out what is actual facts and what is fiction. One of the ways that we do this is called scientific method. So chemistry, as all sciences, are basically going to be based upon a couple of things. It's going to be based upon observations and experimentation, right? We make observations, we make hypotheses. We have this thought. What happens if I add a gummy bear to water? Does it blow up?
Is it gonna get like smushy?
What was that?
Is it gonna get like smushy or? Really
It's going to get
sticky?
smushy, and then over time, it'll probably dissolve, right? In that water, okay? Now, what happens if I put gummy bears in water and I start boiling it?
Then it's gonna spread like a liquid.
So it's going to speed up. It's going to dissolve faster, right? But you have that hypothesis, right? You can test it out, can you not? Erica, how would I test that out? So we have Graciella's hypothesis. How will we test out her hypothesis?
We experimented.
We set up experiments, right? So we plan out, we do our experiments, and then we see if Graciela is going to be right or if Graciela is full of crap, right? So that there is part of the scientific method. We make some observations. We establish a hypothesis. A hypothesis is basically, it's what we kind of are using to try to explain the observations that we see. Now, if we saw gummy bears all of a sudden blowing up, catching on fire, would that prove Graciella's hypothesis or disproves Graciella's hypothesis?
Disproves.
Disprove. Okay, so that's also part of it, right? So the question is, we do those experiments to sit there and figure out whether or not that hypothesis is correct or incorrect. Okay. So I said the word hypothesis. So a hypothesis is just basically how we're trying to explain those observations that we're seeing. First thing that we always start off with is that observation. The next thing that we do are hypothesis. How many of you guys have kids?
Actual kids?
Actual
Yeah,
kids that can talk.
children that depend on you to live.
Yes. If you don't have kids, you have nieces and nephews or cousins that are young.
I actually have two. I have a boy and a girl.
Okay. So did they ever go to you? Daddy, why is the sky blue? Why isn't it green?
Yep, and I tell them I made it that color.
You tell them you made it that color. You're a horrible dad. You realize that, right?
Yes.
You're not gonna even give him God did it that way. You're not gonna at least give him that, You're like, I did it. I'm God. I made it that way. Okay, I see.
Credit for Christmas because of Santa. I'm taking credit for something.
Okay, you're like, okay. So you guys know to tell your children that Carrie made the sky blue. Remember. Okay, so those kids that come to you, and they're so excited, because they made this observation. What was the observation that they made?
The sky is blue.
The sky is blue. And they find it incredible. You know what? That sky is blue. And they're so curious about life. They're so curious about it. And they always ask you, so why does that happen? Why? Why? Right? And what do you tell them? Most of the time, be honest, Oscars, what do you tell your nieces and nephew or children or cousins?
Well, if they ask me that,
Yeah.
what do I tell them?
Yeah.
I'm not sure.
I took
I'm gonna ask that. They're too small. I only have two.
You know what you tell them? You're probably on your Game Boy or your I don't know, your PlayStation or your Nintendo Switch. You're probably there and you're like, leave me alone. Just leave me alone, right?
That's true, yeah.
Yeah, okay. So in most cases, that's what most of us do, or they tell them, well, just because God made it that way, or Carrie made it that way. That's the reason why, right? And then we call it a day. And as adults, we don't want to sit there and think about it. But as kids, we want to know. Now, I'm challenging you to go back to when you're a kid, right? Start off with those observations. Start off with that hypothesis, okay? And it's going to make this class so much better, okay? So let's keep going. So laws of science, basically the way that we determine laws is we've done these experiments and we've checked these experiments and we've done the predictions, we've done these hypotheses and we've checked them and 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 they've held up, right? At the end of the day, the data turns out to be exactly what we hypothesized. That hypothesis then becomes a law because it's been tested over and over and over and over and over and over again. A theory basically is something that is testable, right? And we've done the work and we've tested it out and the explanation tends to hold up. Can you kind of see the difference between laws and theories?
Yes.
Okay, so this is basically the outcome of science, the scientific method. We make our observations, we form a hypothesis, right? And so from our hypothesis, we'll do experiments. If those experiments turn out not to be right, we start the process all over again. We keep the observations, we just reformulate our hypothesis. If our hypothesis is right, we have the results that we're thinking. What we're gonna do is we're gonna write a paper, but we're probably gonna do it a couple of times just to be sure because nobody likes to be wrong, right? Anybody like to be wrong?
No.
Right? No, that's good, I like it. Okay, nobody likes to be wrong. So we're gonna just be sure, And then we're going to share that with the scientific community, right? And then once the scientific community has done all of the testing and it's done independently of us, it has two possibilities. It can either become a theory or it can become a law. Okay? So in the case, your observation becomes a law. Your hypothesis becomes that theory. Okay? Questions? Concerns? Cash?
Gosh.
Oops.
No, he's serious. Don't bet Dr. Henry.
What was that?
I said he's serious. Don't bet Dr. Henry.
That's right. I told you I like money, right? You can Venmo me. And I take credit as well.
How much is
Okay.
an egg?
How much is an egg? So that's going to cost you about $3 million. And that's on the discount. It used to be 10. So
We're
when
never
you're ready to
gonna
pay-
finish paying.
What was that?
We're never gonna finish paying.
No, I don't. You can't pay in installments. It has to be upfront. If I'm gonna get fired, I'm gonna get fired for real. So okay, so let's see. Okay, so when we're talking about science, we can break up things into kind of two major categories, right? Things that we can see and things that we can't see, that we have to use a microscope to see. And then there's a third one, and that's basically things that are so small that we can't even see with a microscope, okay? So we have what we call the macroscopic. Those are things that we're able to see. Macro, they're big, right? Microscopic, meaning that they're so small that we need a microscope to see them. And then here we say symbolic or the particulate. The particulate is so small that we can't see. You guys understand that?
Mm-hmm.
So the particulate. Okay, so give me something that you can see. Judy,
Yeah,
something you can see with your eyes.
you.
Me. I know, I'm so pretty. What can I say?
You so conceited.
Got a couple more minutes, so I'll wait till everybody's here.
You want me to say something else?
No. I want, let's see, Christian. Christian, tell me something that I need a microscope to see.
I don't know, an ant.
Did you say an ant?
Yeah.
You can't see an ant with your eyes? Are you that blind?
I mean, I don't know.
Oh, you do know. Think about it.
Like a magnifying glass?
Well, it's something.
They don't zoom that much.
Well, okay, so something that you would need more than a magnifying glass to see, because technically a magnifying glass is kind of in between, right?
Yeah.
A microscope and your eye, right?
Yeah.
So something that we're going to need a microscope to see. Tell me something I'm going to need a microscope to see.
Like germs?
Like germs. Yeah, that's good. A bacteria cell. Perfect. See, you knew something. Okay. Leslie.
Small organisms.
Small organisms. Okay, so you're like, again, you're talking about like maybe a pathogen or something like that?
Yeah.
Yeah. Okay. So now tell me something that you consider to be a particulate, something that you can't see with a microscope. Abel.
Dead skin.
Dead skin?
Yeah,
Oh.
the dust that floats around.
But can you see that with a microscope?
Yes.
Okay, now I want you to give me something that you can't see with the microscope. It's so small that you can't even see it with a microscope.
Quarks.
Quartz,
Quarks.
as in like the mineral quartz? Or did you say, oh, you're talking about, you didn't say quarks, you said quarks, as in the units that are even smaller than protons and neutrons, right?
Yes.
Okay, yes, okay, yes, that's a good, very, very good example. Okay, so in situations, there are things that we can't even see with a microscope. An atom you really can't see with a microscope. Can you guys see one piece of carbon? Just one individual carbon atom? Abby?
Yeah.
You can?
Wait, can you repeat that question again?
I say, can you see one individual carbon atom?
No.
No. Yeah. I just thought I'd ask because I'm like, damn, you have really good eyes if you can see that one individual carbon atom.
No, I can't.
You put Hawkeye to shame, so. Okay. So now this kind of brings us to the different phases, right? Different phases of matter. So we have we've broken things up into 3 different phases. We have water, right? Which is that a liquid, solid, or gas?
Liquid.
Okay, ice.
Solid.
And gas.
The clouds.
The gas is a gas, right? So here we're able to see all 3 different domains of it, right? Of matter. So how do they differ? H2O, water. In its liquid form, we'd always call it water, right? How does that differ from ice? How does ice differ from steam?
The way the molecules are acting.
What do you mean by how they're acting?
Like in a gas, they're moving everywhere and filling space, and if you're in like a liquid, they go to fill that area. If that makes sense. I don't know if I'm saying that with the right vocabulary.
No, you're doing pretty good. It sounds like you've taken my class before or something like that.
Nope, never.
Never, right? Yeah, so the difference between a solid, liquid, and gas is 2 things. One of the things is the organization of those molecules. The other thing is whether or not they're moving, how fast they're moving, how much they're moving. Okay. Have you guys ever been to a nightclub?
No.
No.
None of you guys? Well, that's right. You guys are, and you're also the COVID generation. You're at that borderline. So you're never going to get a chance to go to a nightclub because they don't exist anymore. You poor thing. Okay, so I won't use the nightclub analogy. Let's see. What analogy can I use?
Into the fair.
I don't know what to use in this case, you guys. Nightclub is the best analogy.
Going to
Anybody
the
been to a nightclub so I can pretend like it?
Yeah.
Okay, or a party. We'll just say a party in general, right? Okay, so then we'll say, so you've been to a party. All you guys have been to a party at one point, right? And you have those friends that are not too social, right? And they have a party and 3 people show up, right?
Mm-hmm.
You've been to places like that? Everybody can agree to that? Okay, so in the case where there's 3 people that are showing up, they're in this really big house, there's all of this room, right? And they can do whatever they want. They can move around and stuff like that. That's kind of like what's happening with the gases. They're moving. They have room to move. And so those gas molecules are just moving all over the place because they have room to move. Liquid molecules, they're kind of tight, right? So that's kind of like your friend who has, medium-sized number of friends, right? And then, so you have a little bit of room to move, right? And then you have that friend that is just like very, very popular. Everybody wants to come to their party, right? That's kind of like your solid. You have no room to move, right? So this kind of brings us to what we call the molecular kinetic theory. Okay, the state of an element, or the state of a compound, or the state of a molecule, right, is going to be dependent on the movement of that element, compound, or molecule. If it's moving a lot and has space to move, that's a gas. If it's moving medium, right, that's a liquid. If it's moving very little, that's a solid, okay? And that's exactly what happens here. The only thing with water is kind of an odd beast. It also forms this nice little structure that kind of captures a little bit of air, which allows it to float, right? So a lot of times water molecules, we all know, ice floats, right? It floats in water, right? Or floats in your Coke or in your whiskey, right? True? Okay. And we know that steam. Have you guys boiled water?
Yes.
Have you guys forgot about the water you were boiling?
No.
Yeah.
No.
It's going to burn.
Yeah.
See, Abby's laughing because she knows she's done it. She's like me. I'll be sitting there working on a project and I'm just going to boil water for a cup of noodle. I come back in, the house is all steamed up and everything like that. And, yeah, you know, so we've all done that, right? So it fills up the entire room. It takes up that entire space. And that's what Maddie was kind of talking about. So what happens in gas is going to take up the space that it is allowed to take up, right? Okay, so let's move on. So we've talked about matter. We've talked about the three major states: solids, liquids, gases. We've kind of talked about solids. They're going to be a defined shape. Your ice cubes, aren't they ice cubes because you put them in this tray that is kind of square? So they fill that shape that they're able to define. Water is going to be able to flow. It's going to be able to take the shape of any container that it's in and able to be moved out as soon as you break that container, right? And gas is going to fill up the entire volume, right? Okay, solid, liquid, gas. Simple?
Yes.
Okay, so there is a fourth, believe it or not, I know we never talk about it, but there is a fourth state of matter. The fourth state of matter is called plasma. So plasma is, the best way of kind of defining it is kind of like gas and gas with energy, right? And that's kind of like the best way of defining it. It's gas that's kind of charged up. It has those particles that are available for it. So that's going to be your plasma. So that's going to be your fourth state. And plasma is basically found in environments of high temperature, and it's also sort of dependent on pressure as well. Okay? And so it's going to be different than gas alone because it's always charged up. And there's a threshold of a charge that's associated with it. Okay? So an example of plasma that naturally occurs, that's going to be like your stars or our sun, lightning, and then we also make plasma TVs, right? Back in the old days.
Andrew, you said plasma is found in pressure and pressure and temperature?
Yes, primarily temperature, but pressure plays a huge part in it as well. But pressure plays a huge part in a lot of things. So this is an example of a plasma torch cutting a piece of metal. Okay, so you know the four states of matter? Let's see. Cynthia, four states of matter. You're there, Cynthia?
Yeah, sorry about that. Can you repeat the question?
What are the four states of matter?
Oh, I know this one. Sorry, just right off the top of my head, it's not coming to me.
Okay. Aldo, you gonna
okay.
help her out?
Yeah, it's solid, gas, liquid, and plasma.
Okay, solid, liquid, gas, and plasma. Okay, believe me, I will always catch you with your pants down, even if you have a black screen. Okay, so mass versus weight. Okay, now this is really important because some of you guys are going to be doing things where we want to take mass in consideration and not weight. Okay, so the biggest difference between mass and weight is mass is the measurement of the amount of matter, right? Measurement of the amount of matter, where weight refers to the force of gravity that's going to be exerted on that matter. So weight deals with force, mass deals with mass of the matter, measurement of the mass, or measurement of the amount. Do you understand? So like for instance, since the gravity on the Earth is different than the gravity on the moon, the weight is going to be different, but the mass is going to be the same. So if you weigh, and it's bad because I just said weigh. If your mass is, we'll say 100 kilograms, okay? So your mass on the Earth is going to be 100 kilograms. What is going to be the mass of you on the moon?
Same.
Same. Okay, so if you weigh 100 pounds on the Earth, is that going to be the same as much as you weigh on the moon?
No, there's no gravitational pull.
No, it's going to be different because the moon is like 1/16 the gravity that it is on the Earth, right? So you're going to be 1/16 less. Okay, now could you imagine putting that in the dating profile? I'm a 200-pound man, right? But when you're on the moon, how much do you weigh? 1/16 of 200 pounds? How many girls are going to be, you know, swiping you left or right based upon that size, right? Not to say women are shallow or anything like that. Men are just as shallow. Okay, so the law of conservation. Now this is going to be important. Now chemistry is founded on this law. Okay, you will see it time and time again. It may be asked to you in different forms, but at the end of the day, it is going to be exactly the same question. If you just boil it down, the question is exactly the same. The statement is exactly the same. The law of conservation of matter, the law of conservation of energy, right? Those two laws, the law of conservation in general. If you guys remember this, and you just think about what I'm telling you, what you put in, you must get out, right? What you put in, you must get out. That's basically the law of conservation, okay? So what that means is, if I'm putting, let's say I'm eating all the time, all that food I'm eating, it has to come out in some way. It's either going to come out in terms of energy, poop, vomit. It's going to come out, right? What I put in, it's going to have to come out, or fat, one or the other, right? So those are, you're going to have to account for it, right? At the end of the day, what you put in, you must get out. It's kind of like we would like our checkbooks to work too, right? What you put in, well, actually, we want to try to keep it in, but you know, a lot of it tends to go out because you have to pay bills. Okay, questions, concerns? Okay, now with energy, that means that the law of conservation says what you put in, you must get out. So that means that energy that you're putting into a system can either be converted, right? It can never be destroyed or made. Do you understand?
Yes.
Okay. So you guys got that? Okay. Now this is going to be true in both physical and chemical changes, right? So we take this bottle of water, we freeze it. Is that going to change the amount of matter that we have?
No.
It's going to be the same amount. The mass is going to be the same. That ice is going to be the same. If we could actually weigh a balloon, we'll say, we'll put all the steam, we'll put and boil all of the water. Say this was a glass bottle instead of and we boil all the water out and put it in a balloon and tie it up. Is the mass of that balloon going to be the same if we subtract the rubber part of the balloon as the mass of the water that's in here?
No, because you got rid of another part of it, so you got rid of the weight of the rubber.
Well, we're neglecting the weight of the bottle. Say when we neglected the weight of the bottle, we're just looking at the mass of the water.
Wouldn't the mass be the same, but the weight would be different?
No, the mass would be the same in either case, and the weight would be the same, because we're on Earth right now. So the gravitational pull is going to be exactly the same. So the mass and the weight are going to be the same in this situation.
Okay.
So that's because we're just weighing the water. We're not taking into account the bottle. And in the case of the balloon, we're not taking into account the balloon. If we're just taking into account the mass of the steam and the water, it's going to be exactly the same. Why is that?
Because what you put in, you have to get out.
Say it again, Maddie.
What you put in, you have to get out.
Okay, so I want everyone to say it. One more time. Everybody at once. Let's see if we can do it together. Turn on your mic. I want to hear it.
What you put in must come out.
What you put in must come out.
Come on.
You put in must come out.
What you put in must come out.
What you put in is what comes out.
Okay. Now you understand that. Okay, we'll see on the test, the very first test. Okay, so law of conservation, right? What you put in, you must get out. So here's a good example. How many of you guys brew beer or make wine? I do.
That's just you.
Just me? Just me. Darn it.
Yeah.
Well, you guys are missing out. I have a whole bunch of wine since none of you guys brew beer or make wine. I have a whole bunch of wine that I'll be drinking by myself. So that's it. Fortunately, I can handle that. So to make beer or to make wine, what I do, I have fruit juice or I have fruit, mix it all up. I add some sugar, throw in some yeast, and let it ferment. Right? Now I can calculate, because I know how much sugar I'm putting into my system. I can calculate how much alcohol I will get out of it. Can I write up the chemical equation? Okay, so this is the chemical equation for fermentation. And this is assuming that we're working with glucose. This is our simplest form of sugar. What yeast does, it'll take sucrose, break it down to glucose, and then go through this process when there's no oxygen available, go through this process of making carbon dioxide and alcohol, ethanol. So if you're making beer, you can get the carbonation put into your beer, and that's provided by carbon dioxide. And you can get your ethanol, right? Pretty simple, right?
Mm-hmm.
Okay. So at the end of the day, we put in glucose. What we get out, we get carbon dioxide and ethanol. How many carbons do I have? Let me help you understand my chemical equation here. How many carbons are here? So this here, okay, thank you, 6. So we have 6 carbon. C represents carbon, there's 6 carbon. This number here represents the number that you have for that carbon in a molecule. This molecule, or this compound, is connected all together, okay? How many hydrogens? H is for hydrogen.
Oh.
How many oxygens?
6.
Okay,
What are
so
you doing, Miss
glucose,
Queenie?
we're breaking down this one glucose molecule into two. This tells me I have 2 carbon dioxide. Have you heard of carbon dioxide before?
Yes.
So isn't that what you breathe out?
Yeah.
Okay, so you've heard of carbon dioxide. So carbon dioxide has 1 carbon and 2 oxygen, carbon dioxide. Okay, so tell me, how many total carbons do I have between my carbon dioxide, and this is the chemical formula for ethanol, or drinking alcohol.
6.
So this has how many carbons?
2.
2.
2 carbons. So this here tells me I have 2 ethanol molecules. So that means a total of how many carbons would I have together?
4.
Okay, so 2 plus 4 is what?
6.
So I have a total of 6 carbons. Okay, so how many hydrogens do I have?
5.
There's 2. Remember, there's 2 ethanol molecules.
10.
So there's 10 plus this hydrogen here, right? 2 times 2 times 1 plus 2 times 5. What is 2?
Okay, 10, yeah.
Okay.
12.
So altogether, I have 12 hydrogens. How many oxygens do I have? So I have 2 times 2 here.
4.
6.
And plus 2, total 6, right? So I have 6 oxygens. This is what I put in. This is what I get out. This is called my reactant. And these are called my products. So we put in the reactant and we get out our products. Is what we put in the same thing that we got out in terms of quantity? I have 6 carbons here. Oops. Let me circle this. I have 6 carbons here. I have 12 hydrogens here, and I have 6 oxygens. Okay, is that exactly what I put in? Did I put in 6 carbons, 12 hydrogens, and 6 oxygens?
Yeah.
Yes.
What is the difference though?
Yes.
What is the difference from what I put in? Why don't I get sugar out?
Because the sugar was used to create carbon dioxide from the yeast.
Because the sugar was used to create. So we're changing that form of that chemical structure. At the same time that we're doing that, we're also breaking bonds that are storing energy. The other thing that you don't see is these bottles get a little warm. They get some heat, and that's a form of energy. So this here is a chemical reaction because we're not getting sugar back out. A physical reaction is just going to give us exactly what we put in, the same chemical formula. Here we have 2 different products being made, not the same thing. Is carbon, have any of you guys have shooken up seltzer water and just taken the air? Or you probably just sprayed yourself in the face.
Salty
Anybody?
water?
Seltzer water.
Oh. No, that stuff
So
tastes
what I want you guys to do is, I want you to shake up a seltzer water, open it up, and just try to suck in the air. That's it. Does that work? Okay, everybody, this is what you want, and I want you to record it, okay? And post it, and post the link, okay? Post it on YouTube, and you send me the link, okay? I want you to do that, okay?
Can you say the water again?
What was that?
Can you say, you said seltzer water?
Yes, seltzer water. I want you to get some seltzer water, shake it all really up, really good, and then open it and try to just suck the air, the carbon dioxide that's going to be coming out. Okay?
You post it first.
Oh, I'm not going to do it. I already know what happens, right? I've done it many times. You guys are going to do that? Anybody going to do it for me?
Some extra credit?
For extra credit? He's already negotiating. You see that, right? Smart man. Okay. Okay, so my point is, in one situation, here we're doing a chemical reaction. Okay, we're breaking things down. Carbon dioxide is not the same thing as sugar. It's changed. We're changing its form. Okay, so for chemical reactions, you're going to get a change of the chemical components. Where a physical reaction, even though if you guys do that shaking, you'll get air coming out, but some of that water is going to be coming out with it, right? That air that's going to be coming out is still going to be carbon dioxide, the same thing that was put into the water. So carbon dioxide, the chemical composition isn't changing. It's still going to be CO2. Okay? So, questions, concerns, Cash? You guys get it?
Yes.
Okay. So, okay. So here is an example of a battery. When the battery is good, you know, we start off with lead oxide, sorry, lead 4 oxide, and sulfuric acid. After a battery goes bad, you end up with just lead sulfate and water. So you go through a chemical change. So this is an example of a chemical change. But at the end of the day, if you balance the chemical equation, you're going to end up with the same number of lead atoms, number of oxygen atoms, and the number of sulfur atoms and hydrogen atoms that you put in that you're going to get out. It's just the chemical compounds have changed. They switch partners in this situation. Okay? You guys understand that? Or is that too much? You're like, God, it's so boring. So let's make it exciting. Okay, so let's talk about elements. Elements.
Oh, Cassie is saying that if we can mute unless we are talking.
Cool. Okay. So element is basically a type of pure substance that can't be broken down into a simpler chemical form. It's the simplest form that you can get. What you see on your periodic table. How many of you guys have gone to P table?
I have.
Okay, so let's go to P table. These are your elements. These guys can't be broken down into a simpler chemical form. And that's going to be kind of important because when we get to nuclear chemistry, it kind of throws wrenches in a lot of things. But that isn't going to happen until the second semester. Although you're going to get a taste of it here in a few weeks. Okay? So carbon. Carbon is an element. Lithium is an element. Sodium is an element. Oxygen is an element. Okay? All of these guys are elements. Now, there are diatomic elements. I'm going to tell you about your diatomic elements. So you want to write these down now. I'm going to give you a little acronym. What is the word? Anagram. So remember. Okay, you guys ready for the anagram?
Mm-hmm.
Have no fear of ice cold beer. Okay? So your diatomic elements are hydrogen, have, nitrogen, no, fluorine, fear, oxygen, of, iodine, ice, chlorine, coal, and bromine, beer. Okay, how many is that? 7?
Again.
Do you want me to say it again?
Yes.
Yeah.
Hydrogen, nitrogen, oxygen, fluorine, chlorine, iodine, bromine.
Someone want to start bromide.
Oh my, it's fast.
Wait.
That was have no
Hydrogen.
fear of ice cold beers, right?
Have no fear
Hydrogen.
of ice cold beer.
I like that.
Oh.
It's hydrogen.
Okay, Dr. Henry, I got hydrogen, nitrogen, fluorine, oxygen, iodine. I need cold and beer. Is it carbon and
No,
bromine?
Chlorine and bromine.
It's all circled on the board. Can you guys see the P table?
Oh,
Yeah,
there
stop
we
sharing.
go.
So it's hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. That one, right?
Yeah.
Okay, it's in order then, yeah.
Okay, you guys see it? It's all circled?
Yes.
Okay, so those guys are called diatomic elements. Diatomic, what do you guys think diatomic means?
Comes in pairs of 2.
2, yeah, 2. So that means that when it's in its natural state, we write hydrogen as H2. There's 2 hydrogen molecules. That's the only way that it's going to exist in its natural state. Okay, that means that oxygen, the oxygen gas that we breathe in, it's O2 because that is the natural state that it exists. Okay, you guys good? Okay, so there are other elements that exist in polyatomic states. One of those is sulfur and phosphorus. We'll talk about that later, okay? So these guys are not diatomic, they're gonna be polyatomic. But let me circle those in different. What do you think polyatomic means?
Multiple.
Many.
Okay, we'll talk about it later. Okay, you guys got that? You know the diatomic elements? All the other ones, when they're all by themselves, right? They will be just that element. They're not diatomic, like barium. Barium will just be Ba, so it's not Ba2. So anytime that you're writing the chemical equation and you have hydrogen gas, you're always gonna write H2. You guys got that?
Oh, yeah.
Okay, good.
Thank you very much.
That'll be 175 bucks.
Duck, got you. I live near a whole lot of ducks. I can get you 105 ducks.
That might actually work out because I could probably sell those for a lot more.
Exactly.
Yep.
Anybody
Okay.
ready?
Okay, so if you actually look on the periodic table, you'll notice that we have a whole bunch of them on there. Let's open that up again. A whole bunch of elements on here, right? Right now, we have basically, I guess we have 118 that we've talked about. There are some that aren't stable enough to exist, and so we don't count them. So they're counted based upon their stability. These last ones, these guys aren't stable. That's partially why they're in that gray tone. They're not stable molecules. They exist very, very short times. Okay? Questions, concerns, Cash? And also they were man-made. They were generated in labs. Hence, the reason why they're not stable. Now, the beauty of it is that we have, as I said, 118. There is the potential of having more elements and discovering more elements. We're only limited by what we can measure and what we can see. So there's room for growth. And that is the beauty of science. There's always room for growth. Okay? Okay, so let me tell you about the periodic table since we've brought up the periodic table. Let me give you a little more insight. Okay, so the periodic table is organized based upon the atomic number. Up here, this represents the atomic number of the element. No element will have the same atomic number. Hydrogen is always going to be 1. The atomic number represents the number of protons that element has. Hydrogen has 1 proton. Carbon. What is that big number up top for carbon?
6.
So how many protons does carbon have?
6.
6.
Again, the atomic number represents the number of proton that element has. Okay? So carbon has 6 protons. And I haven't even told you about a proton. You're probably saying, what the hell a proton? What is a proton? So an atom is made up of 3 parts. And we won't get into quarks in this class, okay? So we have protons, neutrons, and electrons. Protons are positively charged particles. What does positive start off with?
P.
P.
P. And then the next letter?
P.
O.
Wait, what?
Pro. Positive. Okay, P. Okay, so proton, positive. Electron
Negative.
is negative. And neutron.
Neutral.
That's right. Which we know is a 0 charge, right?
Mm-hmm.
Okay. So an element is beautiful because in its natural state, it has the same number of protons and the same number of electrons, right? So they're balancing out. So an element is always going to have a total charge of 0. Okay? You want me to say that again?
Mm-hmm.
An element is going to have a total charge of 0. Okay, so I'm going to see if you guys are good at math here. Okay, so hydrogen has, well, hydrogen's atomic number is 1. How many protons does hydrogen have?
1.
1. So if hydrogen has 1 proton, how many electrons must hydrogen have?
Negative 1.
1.
1.
Negative.
Right? Simple?
Yeah.
Okay. Alyssa, mercury has 80 protons, or atomic number of 80. How many electrons must mercury have?
So like would it have to have like the same number, so it'd be 80?
That is correct. Simple, right?
Yeah.
Okay, good.
Oh wait, there's more.
Exactly. But wait, there's more. Who knew? Who was that?
Cassie.
Okay, Cassie. Okay, so we've talked about the number of protons, let's talk about the number of, we've talked about electrons. Let's talk about the number of neutrons. So the number of neutrons can be determined by the atomic mass of the atom or the element. So in this case, our atomic mass is 1.008. Now, I'm going to tell you this, and then we're going to get into it in 3 chapters about isotopes. But what you want to do is when you see that atomic mass, to determine the number of neutrons, you want to get it to a whole number. So 1.008, is that closer to 1 or is that closer to 2?
1.
1. So the whole number we would probably use is what?
1.
1.01.
1, right? So we're going to use the whole number of 1, okay? So the atomic mass, type this out. Is equal to, I should say, let me change this a little bit. We'll call it the atomic number. Okay, so let me revise it so I'll make sure I'm clarifying it. So we have what we call a mass number. A mass number is going to be the whole number of the atomic number. Remember I told you? So the whole number for 1.008, which is the atomic mass of hydrogen, is 1. So the mass number is going to be what?
1.
1, okay? So let's say we have something like, let's see, cesium, CS. So what is the atomic mass for cesium?
133.
Say it again, please.
133.
1. So is that the atomic mass or is that the mass number?
The mass number.
That's the mass number. So the mass number would be 133, but the atomic mass is going to be
132.91.
132.5. Now you see, I know it seems like a very minor thing, but it's going to make a huge difference here in a second. Okay. Okay. You guys got that so far?
Yeah.
See, how are we doing on time? Getting close to that time. Okay.
Can you run through another example of that?
Yeah, sure. I was going to do another example of that. Let's do chromium.
Linear finding.
Okay, so what is the atomic mass of chromium?
Where is chromium?
51.996.
Okay, the atomic mass is 51.996. So the atomic number for chromium is 24. So you guys can find it. You guys see it?
Yes.
Okay, so what is the mass number for chromium?
52.
52. Okay, so now we're going to establish what mass number is, right?
All right.
Okay, so mass number equals number of protons plus number of neutrons. Protons plus neutrons. Okay, now let's see these skills, right? So the mass number for hydrogen is what again?
52. Wait, what?
Hydrogen.
Oh, no, never mind.
Hydrogen.
Yeah, it's 1. I was
Everything.
looking at chromium.
Okay, so the mass number is 1. How many protons does hydrogen have?
1.
1.
1.
So then how many
1.
neutrons does hydrogen have?
1.
1.
Oh, you guys are such suckers. So you're going to tell me. I don't know. I know it's been a
Weird.
while since I had to do math for a class or anything like that. But you're telling me 1 plus 1 equals 1. Is that true?
No.
No, 2.
That equals 2, right? 1 plus 1 equals 2. That's the last thing I heard. I don't know. You guys are doing some crazy math these days. I don't know. Right? So 1 plus 1 doesn't equal 1. So then how many neutrons must hydrogen have?
0.
0. That's right. So
Moses.
hydrogen has 0 neutrons. So hydrogen has 1 proton. You guys can see if I put over here, I'm just going to put a P there. 1, and I'll put a P plus for proton. So we will know it's plus. It has 1 electron and 0 neutrons. Okay? Simple? Good. Now we'll see, what about chromium? Since we have chromium circled here, how many protons does chromium have?
24.
24.
Okay, so it has, for protons, 24.
24.
Electrons, that little
24.
E minus. How many?
It should be okay. It has the same number of electrons, so it's
24.
4, right?
24. That's right, because it has to be a total of 0 at the end. And number of neutrons.
0.
28.
Oh, so how did you get 28? What's the mass number of chromium?
52. Okay, 52.
52.
So, how many protons does it have?
24.
24.
So you subtract 52 from the 24.
That is correct.
Mm-hmm.
So 52 minus 24 is
28.
simple.
Oh, it's not 30, is it?
Mm-hmm.
Okay, so let's see those skills. What about cobalt?
Let's go look at cobalt because it's right there in all the metals. All right, so atomic number is 27.
Okay, so that tells me what?
Number of protons it has, and the number of electrons.
Okay, 27.
Mm-hmm.
Number of electrons?
27.
27. So it'll be 32.
Okay.
32 neutrons.
Simple.
Way to go, team.
Yep.
Okay. So you learned your first thing in chemistry. Are you feeling good about yourself so far?
Wait, how you got 32 at the end?
Okay, because what is my mass number?
Isn't it? Wait, where is it? Isn't it 59?
59. Yes. Okay, so that's my mass number. 59 minus 27.
Oh, 32.
Good job.
Okay.
Wait,
I was subtracting wrong.
Okay.
So we all make mistakes.
Piece of cake?
Yes.
Good.
I'm turning off my video. I feel like I look extra sleepy.
P is 27.
Okay. So let's move on. We'll talk about ions later. But this is just to give you a little taste of the good stuff. Okay, so we've talked about an atom. So let's distinguish between an atom and a molecule. A molecule consists of 2 or more atoms that are connected by strong forces, which we call bonds, chemical bonds, either an ionic bond or a covalent bond, okay? Ionic bonds are things that are charged with each other. They're plus or minus charge, and they come together that way. Covalent bond means that you're sharing of electrons. We'll talk more about that later on, but the key is an atom is just the smallest part. An element is, in most cases, an atom, except for your diatomic situations, but they're also considered diatomic elements. Molecule are two or more atoms together. Okay, so I'm going to ask you a question. I said that. Is this an atom or a molecule?
Molecule.
It is a molecule. Now, is this an atom, an element, or a molecule? The Na.
An element.
It's an element. Is it an atom?
Yeah.
It's an atom. Is it, okay? Is it a molecule?
No.
No.
No. Oxygen, O2, oxygen gas. Is it an atom, an element, or a molecule, or multiple things?
It's multiple, isn't it? An element and a molecule.
It is an element and a molecule. Okay, so it's an element because that's its natural state. O2 is its natural state. It's considered a diatomic element. It's also a molecule because of what?
Combines two forces or two atoms.
It has at least two atoms, right? Consists of at least two atoms. Okay, so I'm going to introduce you to one more thing. Compound. Compound consists of at least two different atoms. A molecule can be the same atom or it can be different atoms. A compound is going to exist of at least two different atoms. Okay, is this a compound? Na.
No.
No.
Is O2 a compound?
No.
No.
Is CO2 a compound?
Yes.
Yeah.
Okay, simple. Okay, simple. That means yes?
Yes.
Okay. So let's see. If I have NaCl, sodium chloride. Okay, NaCl. Is it a molecule, atom, element, or compound?
Compound.
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 Is it a molecule?
Compound.
Is it a molecule?
No.
No.
What does a molecule say?
Two.
Consists of two.
It consists of two or more atoms. Is this two or more atoms?
Yeah.
No.
Yeah.
So is it a molecule?
Yes.
Yes.
Oh, yes, it is.
So it is a
Okay.
molecule. N2.
Molecule.
Is it a compound?
No.
Why not?
It's two the same thing.
Because it's the same thing. They have to be different for it to be a compound, right? What about no? NO. No.
Compound?
No. Compound.
And a molecule.
And a molecule. Oh, is this an element? Sorry, N2.
Yes.
Is it an atom?
Yes.
It is an atom?
N2.
Is it the smallest form? Smallest
No.
possible?
No.
No.
No. Okay. What about this guy? Ba.
Atom?
Atom and element.
Element.
Yeah.
And an atom?
Yeah.
Piece of cake?
Somewhat.
Now it is.
Okay. Okay, so let's see. Let's see. So this here is a goal. These are goal atoms are all connected. So we've already talked about molecules, familiar with molecules. Now, remember I told you I'll tell you about sulfur and phosphorus?
Mm-hmm.
Phosphorus, one of its natural states. Phosphorus is kind of funky. It has a state where it will just be P by itself, and there's also a state where it's P4. So that's the reason why we say it's poly, right? Sulfur, this is the most natural form of sulfur, S8, okay? So in Chem 2A, we often will just use P, right? For Chem 1A, you should be remembering that phosphorus, the most common element of phosphorus is going to be P4. The most common element for sulfur is going to be S8. So you're going to be using those for your chemical formulas when you just have sulfur alone. And that's going to be important when you start balancing equations and doing chemical reactions. So this is its natural state. So the ones that are circled are the natural state. So sulfur always is going to be sulfur 8. Phosphorus, most of the time, is going to be P4 when it's in its natural state. Okay, you guys got that?
Yes.
Okay, so these guys, again, the 7 I told you about are diatomic, and these 2 are your other exceptions. Okay, I will give you one more exception a little bit later when we get into ions. So make sure you keep track of that. You will see it on an exam. Guaranteed. Okay, so we've talked about atoms, molecules, and compounds. You guys are feeling comfortable with that, right?
Mm-hmm.
Okay, so now let's talk about mixtures and pure substances. So if I tell you I have a bag of sugar, the good stuff, right? The good sugar, CNH sugar, right? Is that a compound? Is it an element? Is it a molecule? Or is it a mixture of things?
Mixture?
Mixture.
Wouldn't be an element?
Okay, let's do it like this. We'll do a little poll real quick. Let me pull something up. Add a question. Will it work? Sorry, it takes a little minute for things to pop up. Okay, my question is, so sugar, C, a bag. And we're not taking the bag into account. So the molecule, is it a molecule? Is sugar? Sugar is C6, or actually it isn't C6, it's C11. Oh, C12, I'm making things up. C12, H.
22.
O11, that's right. So That is the natural state of sucrose, which is the sugar, table sugar that we eat. Is this a compound? Yes, it is a compound. Is it a molecule? Is it a molecule?
Yes.
Yes, it is a molecule. Is it an element?
No.
No. Is it an atom?
No.
Is it a mixture? No, it isn't a mixture. We'll talk about what a mixture is. I'm going to leave you in suspense. We're going to exit this one, and then we're going to go into the lab room so that I can start